Good morning, everyone. We welcome you all for today's webinar, which is LPDDR5 5X Driving Advanced Memory Solution for Tomorrow's Demand, brought to you by the Truechip Memory team. So in today's webinar, the agenda will be as first we will discuss about LPDDR5 and 5X overview. Then how does LPDDR5 5X act as more power saving SDRAM? How does LPDDR5 5X do performance advancements? We'll discuss about LPDDR5 5X memories as power efficiency and sustainability, talking about applications of LPDDR5 and 5X. Also, we'll discuss challenges in development of LPDDR5 and 5X, covering future trends and innovations in LPDDR, and how to verify LPDDR design by Truechip integrated LPDDR VIP. And at last but not the least, about Truechip VIP features and Debug GUI. So let's start with a brief overview of LPDDR5 5X memories. LPDDR stands for Low Power Double Data Rate. So basically it's a synchronous dynamic random access memory, which is also called SDRAM, which transfers the data on both the edges, which makes it even faster than the normal SDRAM devices. LPDDR came into the picture in 2008, which was the first version of LPDDR, mainly targeting the mobile industries and was also called Mobile DDR or MDDR. It is an ideal high-performance solution for mobile applications with a narrow channel width and several low-power operating states. LPDDR5 introduced in 2020, which is a major leap from its predecessors of LPDDR4 and 4X RAMs. LPDDR technology is developed independently of DDR standards in terms of performance, battery life, and data transfer rate. As it was target for mobile devices only, that's why data transfer was clocked with lower frequencies in low voltage in comparison to DDR RAMs, which makes battery life even more long-lasting for mobile devices. LPDDR5 5X standards represent the latest iterations for this technology, delivering significant advancement in speed, efficiency, and functionality. One of the key features of LPDDR is that it achieves a good balance between transfer rate as well as in the cost. It extends the data rate up to 8533 Mbps, operates at ultra low voltage, that is 0.5 volts. So now, generally the main question arises. How does LPDDR5 5X act as more power saving SDRAM than its ancestors LPDDR and DDR SDRAMs? Due to several architectural and operational differences, which are as follows. Lower operating voltage. Reduced voltage signaling, for example, having the minimum differential input voltage for the clock and write clock in all the supported clock rates, and also the operating voltage of VDD getting lesser than the previous generation of LPDDR. In LPDDR5, 5X operates at VDDQ 0.5 volts compared to DDR5 and LPDDR4 4X, which typically runs at VDDQ 1.1 volt and 0.6 volt. LPDDR5 5X comes up with the reduced input-output capacitance for signals such as CK, CA, DQ, and WCK, RDQS, etc. Deep power down and low power states. LPDDR5 5X supports deep sleep mode DSM, write-ex, and data copy functions, allowing unused memory sections to be powered off and saving energy. Power saving can also be achieved by faster and less complex frequency change operation, also called as FSP change procedure, which changes in voltage swings and termination value without ever being in an untrained state, which could result in a loss of communication to the DRAMs. Frequency set points allow the LPDDR SDRAM CA bus to be switched between two different operating frequencies. This is achieved by duplicating all the CA bus mode register parameter as well as other mode register parameters commonly changed with operating frequency. Improve power management. LPDDR5 5X adjusts power consumption based on workload. So, DDR memory is usually designed for desktops and servers with less critical power efficiency. Variable data rate (VDR) and DVFS dynamic voltage frequency scaling. LPDDR5 5X and dynamically adjusts their frequency depending on demand, lowering speed when high bandwidth isn't needed. DDR generally runs at a fixed or semi-adjustable frequency, consuming more power when idle. Going forward, let's see how deep sleep mode, that is DSM, works, which makes LPDDR5 5X as more power efficient. Deep sleep mode in DDR5 saves power by significantly reducing the activity of internal circuits while maintaining data retention due to the following features. It power downs internal circuits by keeping self-refresh operations active, which makes the data retain in each physical layer parameters, and that is like temperature. It reduces the voltage and current consumption. It extends self-refresh intervals. It disables on-die termination, which is ODT. It supports clock stoppage. It supports longer entry and exit latencies. Okay, so here you can see the state diagram for deep sleep mode, which consists of four states, that is self-refresh, power down, deep sleep mode, self-refresh mode, and idle mode. Like if we start with the idle state, it can be go to the further three state as well. Deep sleep mode state via DSM command, it will go to the deep sleep mode state, through which it can go to the self-refresh power down state, or it can go to the self-refresh mode via self-refresh entry command, and it can go to the self-refresh power down state via self-refresh entry power down command. Now another state is self-refresh mode. From here it can go to three states, that is it can come back to the idle state via self-refresh command, exit command, or it can go to the self-refresh power down state via power down entry command, and it can go to the deep sleep mode through DSM command. Then there comes the another state, that is self-refresh power down. From there it can go to the one of the states. Either it can go to the self-refresh mode to power down exit command. Then comes the deep sleep mode, through which it can go to the self-refresh power down state only. From self-refresh mode it can go either to the self-refresh power down, or deep sleep mode, or idle state via self-refresh exit command. So now we will talk about dynamic voltage frequency scaling, DVFS. It saves the power by reducing the supply voltage to the processor or memory when full performance is not required. Lowering the voltage significantly reduces energy usage. So the power dissipation in digital circuits actually follows this formula, which is P equal to C into V square into F. So in this formula, C stands for capacitance, V stands for supply voltage, and F stands for clock frequency. Minimizing dynamic power consumption, adaptive performance control. So there are two modes in DVFS. First is DVFSC mode and another is DVFSQ. So let's first start with DVFSC. So here it consists of two modes as well. First is DVFSC core and another is enhanced DVFSC core. So DVFSC mode supports data rate up to 40 Mbps to 1600 Mbps, whereas enhanced DVFSC supports up to 32 Mbps. And enhanced DVFSC mode is only supported on LPDDR5X. During enhanced DVFSC mode, normal DVFSC write link ECC and read link ECC should be enabled. For enhanced DVFSC mode, supply voltage for CK and WCK can be changed. So here is the below wave form diagram for DVFSC, in which VDD to high and to VDD to low transition has been shown. Here we can see in the diagram that for DVFSC mode, their differential clock signal named as CKT and CKC, command address port named as CA, followed by strobe signal, that is WCKT and WCKC, followed by DQ port, which is bidirectional, on which data will be transmitted, followed by voltage switching from VDD to high to VDD to low. On the basis of FSP switch with VRCG on, which is voltage reference current generator. Here you can see there is a command address strobe, that is CAS, followed by the write command, after which a write latency is applied and data has been driven on DQ bus after this latency. Here you can see the MRW mode register 1 command and MRW mode register 2 command, which comes up with the FSP switching with VRGC on. FSP is like nothing, but it's a frequency set point. So we can see a voltage transition from VDD to high to VDD to low. So after the time duration of TFC delay from the last MRW2 command, you can see there is the MRW1 and 2 command with VRCG equal to off, followed by activate command. So the another mode was DVFSQ mode. In this, where device can allow the VDD queue to ramp up during operational, including read and write operations. And if the operation will be halted during VDD queue voltage ramp, the device must be placed in power down mode or chip select held low until the voltage ramp is complete. ZQ recalibration is recommended before high speed operations. FSP change to appropriate new settings should be done before starting operations at new level. Here we can see the below waveform, in which we can see MRW1 and MRW2 command, which comes up with the FSP switch. With voltage reference current generator enabled, the followed by MRW1 and MRW2 command with configurations of mode register 16 with opcode 6 equal to 0, which makes VRCG disabled, followed by MRW commands to the ZQ reset, followed by the ZQ stop to perform the calibration. After which we can see the transition of VDDQ from low to high. Let's talk about LPDDR5, one of its major feature, that is write X operation. Write X operation in LPDDR5 5X saves power by optimizing write operation and reducing unnecessary data transfer. It can be operated on an activated bank without WCK to CK synchronization and data input to the SDRAM DQ pins. In this case, WCKT and WCKC, that are write strobe signal, required to be valid and complement level after TWR delay to WCK from write command. Additionally, toggling input to the WCKT and WCKC is possible, but the toggling input does transfer the SDRAM internal WCK clock tree at non-WCK to CK sync state, through which we can reduce bus activity as compared to the normal write operation mode. Lower data movement also decreases switching power on the data bus. Optimize write timing, avoiding overwriting of unchanged data. In normal writes, even if only a few bits change, the entire memory block is rewritten, consuming extra power. Integration with power down states. Write-X can be used in conjunction with deep sleep mode and other low power states, further enhancing energy efficiency. So let's go with an example for the write-X operation. Here we can see that the DQ is divided into lower byte and upper byte sections, where the lower byte comes up with DQ 0 down to 7 and upper bytes with DQ 8 down to 15. In this diagram, we can see the DQ data are same for each burst in lower and upper byte, due to which it asserts write-X operation signal. So now the point comes, if DQ are same, so the data can be either 0 or 1. So how memory will get to know about the data? So if all bits in the lower byte are 1, then WXSA in the write-X command, which is driven by the controller, with value 1, else it will be 0 as well. And if all the bits in the upper bytes are 1, then WXSB in write-X command, which is driven by controller, with value 1, else it will be 0 as well. Going further with operational diagram of write-X operation in SDRAM. Here we can see the cache command followed by the write-X command, through which the write latency followed by BLN max plus post-ramble timings are applied, during which we can see the WCKT and WCKC are being in their state without toggling, and there is no transaction on the data. Only DQ bus, through which we can achieve the power efficiency. Now going further, let's talk about another key features of LPDDR5 and 5X, which is data copy. The data copy function in LPDDR5 reduces power consumption by leveraging repeated data patterns to minimize input-output activity and core power consumptions. It includes two power operations: write data copy WDC and read data copy RDC. Reduces input-output activity. Fewer data lines toggle, leading to lower power consumption. Minimizes internal memory writes reads. Less switching activity inside the memory core. Optimized for lower power applications, ideal for mobile and embedded systems where energy efficiency is critical. LPDDR5 write data copy function is applied to 8-byte data granularity per DQ byte. Whenever any data pattern is repeated over 8 bytes of data, only the reference data is transferred through the DQ link. DQ0 for lower DQ byte, DQ8 for upper DQ byte. Per DQ byte from a host to the LPDDR5 DRAM. LPDDR5 DRAM recovers the original 8-byte data by copying the reference data to other 7 DQ data. during LPDDR5 DRAM's internal write operation. In the below diagram, 8 bits of data are same. So here we can talk about the first column in which DQ7 to DQ0 are same B, which only the data will be transmitted on DQ0 and same will be proceeded further for each column. So let's talk about how write data copy function will be performed in brief. So initially, host, that is the controller, issues write data copy, after which it checks the DQ and generates these DC signals on which bit data copy function has to be performed, after which it sends DQ and DQS to the memory. So here is the flow chart where we explain that how write data copy function will be performed inside memory. So initial memory will receive the write command and check DC. It's 1 down to 3, either is 0 or not. So if it is 0, then it will proceed for normal write operation, and DC 1 is to 3 not equal to 0, then it will proceed for write data copy function, where it will check each DC for the bits in which data copy function has to be performed, or keep the original data for each bits. Initially, it starts with DC0. If it is 1, then DQ for each bit in the first 8 bits is either all 1 or 0. And if DC0 equal to 0, then it will keep original data for first 8 bits. Same procedure will be followed by DC1, DC2, DC3, through which it will finish the data copy function. Talking further about how does write data copy reduces the power. So first is minimize external bus activity, which reduces full write read cycles through the CPU. Second is reduce active power usage via fewer bus toggles and memory refresh operations. And the third is avoid redundant data movement, in which the direct internal SDRAM copy instead of transferring to an external computer. Now let's understand deeply with the help of waveform how write data copy function being performed in memory. So here we can see the cache command followed by the write data copy command with DC0 and DC2 equals to 1 and DC1 and DC3 equals to 0. It means for the first 8 bits and third 8 bits, the data copy function will be performed via toggling of DQ0 and DQ8 for lower and upper byte. Only so we can see in the diagram for the first 8 bit and the third 8 bits, only DQ0 has been toggled, rest are low. And for the second 8 bits and fourth 8 bits, whole DQ are being toggled. So previously we had discussed write data copy function. Now let's discuss about the read data copy function. Like it's quite similar to the write data copy function, except that the usage of DC variable for read data copy uses data mask, that is DM pin, to showcase that whether data copy function is hit or miss for the particular bits. So initially, read data copy function command issues the controller to the memory, which checks DQ and generate DM signals. So LPDDR5 5x supports two bus lengths, that is 16 and 32. For bus length 16, it has two 8 bits, whereas for the bus length 32, it has 4 8 bits. So when all DQ in a single bit out of 8 bit group are equal to DM bit is asserted. For DM0, first 8 bits, from DM8 second 8 bits, from DM16 third 8 bits, and DM24 for last 8 bits. So Below is the waveform about read data copy. Here we can see the cache command followed by read command through which read latency has been applied. So after the read latency, we can see the data on the DQ bus, in which the first 8 bit and the third 8 bit are of the data copy, in which DQ0 is toggled for first and third 8 bits. For lower byte and DQ8 are been toggled for first 8 bit for upper byte, whereas the second 8 bit, fourth 8 bit, the DQ is being toggled. So let's talk about the performance advancements in LPDDR5 RAMs. We have improved bandwidth efficiency. LPDDR5 came up with 3 banks architecture, that is the 16B mode, 8B mode and bank group mode. While in the case of LPDDR4X memories, which comes up to 8 bank architecture only. 16B mode, which consists of 16 banks, as this mode doesn't consist of bank group and supports both burst lengths of 16 and 32. Along with the 16B mode, support 2:1 and 4:1 CKR write clock to clock. It supports maximum data rate of 3200 Mbps. Now you can see on the diagram how the architecture of 16B mode is being designed. In this diagram, there is a CA bus and there are 16 banks distributed for DQ bytes data. Talking about 16 burst lengths data on X16 pins, where the total data to be stored is 256 bits, out of which 128 bits will be stored by the DQ byte 0 and another half of 128 bits will be stored by DQ byte 1 inside the memory bank. Bank group mode, which consists of 4 banks and 4 bank groups and supports both burst lengths, that is 16 and 32. Along with the bank group mode supports both 2:1 and 4:1 WCK to CK ratio, which we will discuss in upcoming slides. It supports maximum data rates of 6400 Mbps. Only the bank group mode can support BL32, which is burst length 32, in the interleaving fashion in case of 4:1 CKR, write clock to clock ratio. Now you can see on the diagram how the architecture of bank group mode is being designed. In this diagram, there is a CA bus and there are 4 banks and 4 bank group distributed for DQ bytes data. Talking about 16 burst length data on X16 pins, where the total data to be stored is 256 bits, out of which 128 bits will be stored by DQ byte 0 and another half of 128 bits will be stored by DQ byte 1 inside the memory bank. 8 bank mode, which consists of 8 banks, as this mode doesn't consist of bank groups and only supports burst length of 32. 8 bank mode supports is only present in LPDDR5 SDRAM and are not supported in the case of LPDDR5X SDRAMs. Along with that, 8 bank mode supported only a 2:1 write clock to clock ratio. It supports maximum data rate of 3200 Mbps. Now you can see on the diagram how the architecture of 8 bank mode is being designed. In this diagram, there is a CA bus and there are 8 banks distributed for DQ bytes data. Talking about 32 burst length data on X16 pins, where total data to be stored is 512 bits, out of which 256 bytes will be stored by DQ byte 0, where 256 bits will further be divided into 2 groups of 128 bits, which will be stored inside memory banks, and another half of 256 bits will be stored by DQ byte 1 inside memory bank in the same manner as DQ byte 0. So we will be looking to the clock architecture. Here is the below example of LPDDR4 in which single clock from the SoC DRAM of 2133 MHz. Clock frequency same as DQS of 2133 MHz. CA bus is SDR, which is single data rate with same Mbps. Data bus is DDR of 4266 Mbps. Now let's see the clock architecture of LPDDR5. Clock for CA is 800 MHz, WCK and RDQS are of 3200 MHz. CK to WCK ratio is 1:2 and 1:4. CA bus if DDR of 1600 Mbps, data bus is DDR of 6400 Mbps. So let's talk about more of the performance advancements in LPDDR5. Enhanced reliability. It comes up with the ECC error correction code, which provides robust error correction for increased reliability in automotive and industrial applications. Increased data rates. It offers data rates up to 8533 Mbps as compared to LPDDR4X 4266 Mbps. Enhanced scalability. LPDDR5 5X is designed for smoother integration with advanced process nodes, example 3nm or 4nm SoCs, and multi-core architectures making it ideal for flagship devices. About power efficiency and sustainability of LPDDR5 RAMs. The LPDDR5 memory is designed to meet the demands of modern applications while prioritizing power efficiency and sustainability. These technologies have been optimized to deliver high performance with significantly reduced energy consumptions, aligning with the growing emphasis on environmental sustainability and energy consumptions. Sustainability benefits of LPDDR5. Reduced energy consumption across devices, extended battery life, lower heat generations, efficient resource utilization in data centers, support for edge computing, minimized e-waste. So let's discuss about applications of LPDDR5 RAMs. First is mobile devices. Smartphones, tablets, and ultra-thin laptops benefits from higher speeds and energy efficiency. Automotive systems. Automotive driving systems and infotainment require fast, reliable memory for data-intensive tasks. AI and IoT devices. LPDDR5 provides the bandwidth and efficiency needed for edge computing, AI model interference, and IoT devices. Gaming. Enhanced memory speed delivers smoother performance for mobile and handheld gaming consoles. So let's talk about the challenges in development of LPDDR5 RAMs. Design and compatibility. High-speed interfaces. LPDDR5 advanced with speed of up to 8.533 GT per second than LPDDR5, which is 33%, due to which it requires careful design to maintain signal integrity while minimizing noise, jitter, and crosstalk. Backward compatibility. Ensuring compatibility with legacy system adds complexity. complexity, power and thermal management, balancing power and performance. Achieving low power consumption without affecting power performance is critical, especially for mobile devices. Efficient cooling solution. High operating speeds can increase temperatures requiring effective thermal management. Further about challenges in the development of LPDDR5 RAMs. Manufacturing and yield. Shrinking processes nodes to improve density and power efficiency increases complexity in manufacturing and reduces yields. Verification and validation complexity. The verification of validation of LPDDR5 systems are among the most challenging aspects of development due to their high speed operation, complex protocols, and stringent power efficiency requirement. Now let's talk about future trends and innovations in LPDDR. Evaluation in LPDDR5X and beyond. In April 2024, Samsung Electronics announced development of LPDDR5X 10700. It is capable of operating at speed up to 10.7 Gbps. It provides a 25% increase in bandwidth and improved power efficiency, supporting high-speed data service applications such as 5G AI and the metaverse. Integration with 5G and AI applications. The rollout of 5G networks and the rise of AI applications require more memory solution that can handle increased data volumes and fast communications. LPDDR5 addresses these needs by providing the memory bandwidth and responsiveness needed for 5G enabled devices and AI driven functions in smartphones, smart cameras, and IoT devices. Further talking about future trends and innovations in LPDDR. LPCAM, Low Power Compression Attached Memory Module. It is a groundbreaking technology which has the potential to redefine the DRAMs market for PCs, laptops, and possibly even data centers. LPCAM tackles the limitation of SODIMMs by offering high capacity modules that scale up to 16 GB to 128 GB. LPCAM is a detachable module offering enhanced flexibility for PC and laptop manufacturers. It is the promising up to 50% improvement in performance and 70% in power efficiency, all the while occupying 60% less space on the motherboard compared to SODIMMs. LPDDR6 increased data rate with 8.8 7.16 Gbps per pen. LPDDR6 is currently in the early stages of development with industry adoption expected by 2026 to 2027. So how can we verify LPDDR design using Truechip integrated VIP? Here we can see the architecture of LPDDR5 VIP. From the left hand side, it starts with sequences with basic plus error injection test case blocks, through which transaction of AXI is transmitted to AXI master and transaction of AHB or APB to AHB or APB master, which are in sky blue and dark blue color. From these two master, transaction is transmitted further to the AXI APB AHB converter via AXI interface and AHB APB interface depending on the signal type. As AXI interface is also connected to two components, the first one is the AXI monitor, which works as a protocol checker and shoots the error in case of protocol violation. The second one is the AXI scoreboard, which is used to check integrity in case of writing and reading. Along with the APB interface is also connected to the APB monitor, which works as a protocol checker and shouts the error in case of protocol violation. Once the transaction is received by the AXI AHB APB converter, it will convert the transaction into LPDDR5 form, which is a light purple color, through which the transaction is being transferred to the memory controller, which is also in light purple color via protocol interface. Through the memory controller, transaction will go further to DFI5 through DFI interface, and from the DFI5 transaction will go further to memory, or we can say LPDDR5 memory via LPDDR5 interface. As DFI interface is also connected to two components. One is the DFI monitor, which acts as a protocol checker and shouts the error in case of protocol violation. And the other component is the DFI scoreboard, which checks the data integrity, not only the DFI interface, but for the LPDDR5 interface as either data which was in DFI interface and transmitted from DFI5, either same or not, and vice versa. For LPDDR5 interface is also connected to two components. One is the LPDDR5 monitor, which acts as a protocol checker and shouts the error in case of protocol violation. And another component is LPDDR5 scoreboard, which checks the data integrity. Through the LPDDR5 interface, transaction is transmitted back to DFI5 and from DFI5 to memory controller via DFI interface, from which it goes to the converter via protocol interface, which converts into AXI AHB APB format and transmits further to AXI and APB interface. For integration perspective, integration can be done in easy manner for each component. For example, memory controller. The user can add its DUT controller in the Truechip environment just by disabling the Truechip memory controller and enabling their own DUT with a signal connection. Integration can also be performed in user test bench by adding Truechip controller with a signal connection. The same thing can be done by the PHY and memory as well. Let's talk about the verify design, how to verify design via two-chip integrated VIP. Protocol compliance verification. It ensures the duty design meets JDAC standards. Functional verification. Validate the correctness of memory controller PHY memory operations under expected workloads. Performance validation. It verifies bandwidth, latency, and throughput at peak and typical operating conditions. Power aware verification. Ensure the system manages power efficiency during low power mode. Example, self refresh, power down, etc. Stress and corner testing. Identify issues under extreme conditions. Now let's talk about Truechip VIP features. Here are the differentiating features of Truechip VIP model. LPDDR5 5x memory with all compliant vendors. Supports density up to 32 GB. X16 and X8 DQ signals. 4 banks and 4 bank groups, 16 banks and 8 bank modes. MR8 to switch between LPDDR5 5x SDRAM. All LPDDR5 5x speed grade speed bins. All LPDDR5 mode registers. Direct refresh managements. RX offset calibration. Trainings. Capturing of all the valid commands as per the specification. Data bus inversion and data masking. Programmable write read latency timings. All LPDDR5 5x trainings. Power down features. All timing delays ranges in one model minimum and max. Error injection scenarios. extensively detailed simulation and debug logs, error ID mechanisms, spec section in description of the obtained errors, constrained randomizations, callbacks in host device for user processing of data, built-in coverage analysis, graphical analyzer for easy debugging, transaction logger that prints all the logging information, functional coverage for complete LPDDR5 features. Here comes the Truechip patent TrueEye GUI, which is a Truechip graphical user interface through which user can easily perform integration, easy debugging, and easy searching regarding the VIP required field. Example time, easy error detection, and easy configuration. Let's talk about the detail regarding TrueEye GUI. So there are lot of parameters on which GUI works, out of which some of them we will discuss here. The first one is decoding not required. It provides decoded packets, handshake state machines, and command information for transaction level debugging. Its key advantage is easy debugging. Second is configuration. It allows the user to configure the VIP BFMs and create modified tests in a graphical way. Bypassing incorrect configs, its key advantage is easy configuration. Third is attribute searching. Search the result required field, time, commands, errors, configs, etc. Its key advantage is easy search. Fourth is error detection. Provides information on error with their probable cause. Its key advantage is easy error detection. Fifth is automated integration. GUI reduces the main efforts by giving the user an option to automate the integration process. Its key advantage is easy integration. Sixth is debug time. GUI reduces the debug time up to 50% and speed ups the process. Its key advantage is save time. Seventh is reduced efforts. Engineers with less experience can successfully debug with ease based on useful into the form of GUI. Its key advantage is resource optimization. Last but not the least, utilization summary. Bus utilization and idle time summary for the performance of the device. Its key advantage is enhanced performance. So there are some examples of GUI. You can see a transaction view which comes up in a tabular form, as the first column represents the time in a picosecond and the second one column represents the rank, as this will be helpful in case of multi-rank. Then comes up with another column named as bank. Then comes another column named as command. After command column, then comes up row address column, and then comes up the column address column, followed by data column. As you can see, multiple commands have came one after the another with time scale. First command is mode register 1 command, which comes up at 3071268 picosecond. Then comes mrw2 command at 3086194 picosecond. Then comes up multiple mrw commands mode register write. So as this tabular form consists of another page as well, which consists of bank address, bank group, address, etc. as well. Then comes up the transaction view with error informations. Like we have run a test and there comes a UVM error, and we have to see at what time and what error has been occurred. So this representation will show each and every information regarding that error with its expected and actual value, means that what was expected value as per the specification and what value has been received by the monitor at what time scale and on which command with multiple more field as per the error, which play a vital role in debugging easily. On the right hand side, you can see the error details that show the error ID that popped out. Actually, Truechip designed the check on the basis of error IDs in order to easily tackle which error ID represents which protocol violation. On the left hand side of the transaction view, you can see the red color row that shows an error has been caused due to this. Now let's talk about another feature of GUI, that is transaction view with fatal monitor errors masked into info. Sometimes there comes an error for a particular scenario and the user wants to mask the error from UVM fatal to UVM info. For any reason, the user can also change to warning or fatal right now. We will talk about error masked to info. So as you can see on the right hand side in the error detail section, TC LPDDR5 monitor error 19 has been masked, which is the light gray color for MRW command timing at 5484282 picosecond. So this is how masking can be performed by using GUI. Thank you very much.